Welcome to this lecture on the cumulant generating function. In probability and statistics, we often need to understand the fundamental characteristics of a data set, like its center, its spread, and its shape. While you may already be familiar with moments, today we are going to introduce a more refined, elegant tool that isolates these characteristics perfectly. By the end of this video, you will understand exactly what cumulants are, how to generate them, and why they make complex statistical problems surprisingly simple. Before we look at the math, let us understand why this concept matters. Imagine you are trying to describe a person's physical fitness to a doctor. You could give them your total body weight, but that number includes fat, muscle, bone, and water all mixed together into one messy value. This is exactly how the moment generating function behaves in statistics. It gives you raw moments that mix the center, spread, and shape all together. The cumulant generating function solves this. It takes that tangled information and extracts pure, independent descriptors called cumulants, giving us a much clearer picture of our distribution. Now that we understand what a cumulant generating function is conceptually, let us look at its formal mathematical definition. The formula is beautifully simple. The cumulant generating function, denoted by a capital K, is defined as the natural logarithm of the moment generating function. Why a logarithm? Because logarithms magically turn complex multiplication into simple addition, which simplifies our mathematics tremendously. In this formula, the variable t is just a dummy mathematical placeholder used to help us generate the values we need. It has no physical meaning on its own, but it is essential for the calculus we will do later. To visualize this process, let us walk through the pathway shown in this diagram. We start on the left with our basic probability distribution. From there, we take the expectation of the exponential term to find the moment generating function. As you can see below that box, this gives us our raw moments. But we do not stop there. By passing that moment generating function through a natural logarithm, we arrive at our final destination on the right, the cumulant generating function. This final box is what yields our pure cumulants, stripping away the mathematical clutter. Now that we have our function, how do we actually extract those cumulants from it? Just like the moment generating function, the cumulant generating function can be expanded into an infinite series. We do this using a Maclaurin series expansion. This technique represents our function as an infinite sum of terms, calculated from the values of its derivatives at 0. Hidden inside this infinite series are the individual shape descriptors of our distribution. Each term in the series contains a specific cumulant, waiting to be unlocked through basic calculus. This brings us to the exact formula for extracting any cumulant we want. To find the rth cumulant, represented by the Greek letter kappa, we simply take the rth derivative of the cumulant generating function with respect to t, and then plug in 0 for t. This is exactly the same calculus process we use with the moment generating function to find moments. If we want the first cumulant, we take the first derivative. For the second cumulant, the second derivative, and so on. As the order of the derivative increases, we uncover deeper physical properties of the distribution's shape. Now that we know how to calculate cumulants, we must connect these mysterious values back to the descriptive statistics you already know. The first cumulant is exactly equal to the mean of the distribution. It tells us where the exact balancing point of the data is located. The second cumulant is exactly the variance. This is where the magic of this function shows its true value. It gives us the variance directly. A larger variance means the data is widely scattered, while a smaller variance means the data is tightly clustered around the mean. Moving beyond the mean and variance, the higher cumulants describe the physical shape of the probability distribution. The third cumulant is exactly equal to the third central moment, which measures the asymmetry of the distribution. If the distribution is perfectly symmetrical, this value is exactly 0. The fourth cumulant isolates the tail heaviness of the distribution. It is equal to the fourth central moment minus 3 times the squared variance. This specific mathematical combination completely removes the influence of the variance, allowing us to look at the shape purely on its own. Let us see exactly how the third cumulant is used to calculate skewness. Skewness tells us if the data leans heavily to the left or the right. The formula takes the third cumulant and divides it by the second cumulant raised to the power of 1.5. If this calculated value is 0, the distribution is perfectly symmetrical. If the value increases and becomes positive, it means the tail of the distribution extends far to the right, indicating that there are rare but very large positive values in our data. Similarly, we use the fourth cumulant to calculate excess kurtosis. Kurtosis tells us if the data has thick, heavy tails or thin, light tails compared to a standard normal bell curve. The formula divides the fourth cumulant by the squared second cumulant. A standard normal distribution has an excess kurtosis of exactly 0. If this calculated value is positive, the distribution has heavier tails and a sharper peak than a normal distribution. Physically, an increase in this value means that extreme outliers are much more common in your dataset. Now that we have seen the formulas for extracting cumulants, let us prove that they actually work by deriving the cumulants for a normal distribution. Our goal in this first chunk of the proof is to set up the cumulant generating function. We start with the known moment generating function for a normal distribution, which has an exponential base raised to a power involving the mean and variance. It looks quite complicated at first glance. However, by applying our definition and taking the natural logarithm, the exponential function and the logarithm completely cancel each other out because they are mathematical inverses. This brilliant simplification leaves us with a beautifully simple quadratic equation, which is now perfectly ready for differentiation in our next step. Continuing with our derivation, we will now find the first cumulant. To do this, we take the first derivative of our simplified quadratic function with respect to t. The derivative of the first term is simply the mean. For the second term, the power rule brings down the 2, which cancels out the fraction, leaving us with the variance times t. Finally, to extract the pure cumulant, we evaluate this derivative exactly at t equals 0. By plugging in 0, the second term completely vanishes. This proves mathematically that the first cumulant is exactly the mean of the normal distribution, just as we established earlier. In this final step of our proof, we will extract the second cumulant. We do this by taking the second derivative, which means differentiating our first derivative result. When we differentiate, the constant mean disappears entirely because it has no t attached to it. The derivative of the remaining term is simply the variance. Notice that there are no t variables left in the equation at all. Because of this, plugging in t equals 0 changes absolutely nothing. We have successfully proven that the second cumulant is exactly the variance. This demonstrates exactly why the natural logarithm makes isolating these properties so incredibly efficient. So we have proven that the cumulants perfectly match the mean and variance. This brings us to one of the most powerful properties of the cumulant generating function, how it handles the addition of independent random variables. Imagine you are packing a suitcase for a trip. The total weight is simply the sum of the individual items inside. If you want to find the probability distribution of that total weight, multiplying moment generating functions together gets very messy. But because logarithms turn multiplication into addition, the cumulant generating function of a sum is simply the sum of the individual functions. Let us look at the mathematical formula for this additive property. The formula states that the cumulant generating function of the sum of two independent random variables, x and y, is exactly equal to the function of x plus the function of y. This means that to find the cumulants of a combined total, you just add the individual cumulants together. The mean of the sum is the sum of the means, and the variance of the sum is the sum of the variances. If the variables are not independent, this simple addition rule does not apply. Before we conclude, let us see this additivity property in action with a concrete numerical example. Suppose we have two independent random variables, x and y, both following a Poisson distribution, which models events happening in a fixed time. Variable x represents emails arriving at a rate of 3 per hour, and y represents emails arriving at a rate of 5 per hour. We want to find the distribution of their sum. We start by writing down the generic moment-generating function for a Poisson distribution, and then we take its natural logarithm to find the generic cumulant-generating function. Continuing with our example, we now substitute our specific rates into the generic formula. For variable x, the rate is 3, and for variable y, the rate is 5. Because the variables are completely independent, we simply add their cumulant generating functions together. We place the two expressions side by side, factor out the common exponential term, and add the numbers 3 and 5. The resulting function is exactly the cumulant generating function of a Poisson distribution with a new rate of 8. Physically, this proves that the total emails received simply follow a combined rate of 8 per hour. We have covered a lot of ground today, so let us review the key takeaways. First, the cumulant generating function is the natural logarithm of the moment generating function, designed to strip away mathematical clutter. Second, it gives us direct access to pure shape descriptors, the mean, variance, skewness, and kurtosis, without having to subtract lower order moments. Finally, its additive property makes dealing with sums of independent variables incredibly intuitive. You now have a complete understanding of how to extract and use cumulants to analyze probability distributions.